Ductility, the ability of a material to bend, stretch, or distort before it breaks, before the material fails. The length increase of a material being stretched is known as the elongation, deformation, or the change of length or stretch. The reduction in length from compressive force is also known as deformation, contraction, or change of length. The percent elongation, strain, and elasticity are common measures of ductility. Percent elongation. This is equal to the maximum amount of deformation divided by the original length, and then it's converted to a percentage just by multiplying it by 100%. So the percent elongation equals the deformation divided by the original length, all of that times 100%. So what would be the percent elongation of a bar that is 20 inches in length and it stretches 2.5 inches before it finally fails and breaks? Use your formula. So you should come up with 2.5%. If you didn't, strain. Strain is the ratio of deformation divided by the original length. 2.5 divided by 20, as in the previous slide, equals 0.125 inches per inch. It is the same formula as percent elongation without multiplying the 100%. So, what if a bar is 5 inches and it stretches to 6.5 inches during testing? What is the strain? The answer is 0.3 inches per inch. And again, if you don't get that, go back and rework that formula. Elasticity and plastic state. Now again, the elastic behavior is when a material is stretched, and when the load is removed, it returns back to its original state, like a rubber band. Plastic behavior happens when the material retains deformation after the load is removed. Malleability is a form of plasticity and is needed in forging and extrusion operations. Most ductile materials are malleable. Elastic deformation is the recovery of the original dimensions of a deformed body when the load is removed, and that is known as elastic deformation. The limiting load beyond which the material no longer behaves elastically is called the elastic limit. It occurs when weaker forces, lesser than the object's elastic limit, are exerted. For this reason, an object undergoes elastic deformation before plastic deformation. It occurs because the atomic bonds are stretched when the load is applied so that they can return to their original positions after the load is removed. There is more change in an object's size or shape if the force applied on it is increased. Since elastic deformation does not cause permanent atomic change, it does not contribute to the strength of metals. Perfect elastic deformation is never observed in actual practice because the 100% reversal of an object's dimension is not possible, even with the smallest of forces. So an example, when a stretched rubber band regains its shape after it is released. Plastic deformation. If the elastic limit is exceeded, the body will experience a permanent set of deformation when the load is removed. A body which is permanently deformed is said to have undergone plastic deformation. It occurs when the bonds between the atoms are broken and new ones are formed, making reversal to the original shape impossible. In the change in an object's dimension, strain does not directly correspond on how much force is applied on it, stress. Until a particular limit, plastic deformation forces atoms to move and occupy microscopic defects in the metal, making it tougher. This property, known as strain hardening, is used in industries to strengthen metals and polymers. Plastic deformation proceeds in distinct stages. The first stage, it leads to strain hardening, following by necking. Necking is a narrowing of the object. And finally, the fracture of the object at the narrow portion, if the force is continuously increased. Then you have material failure. In plastic deformation, most of the energy given to a solid in the form of the force that's applied on it is given off as heat, while only a small part is used in exchanging its dimensions. An example, when you bend a metal coat hanger back and forth, back and forth, back and forth, it never really regains its original shape, and then heat starts to develop where it's bending at, and eventually you have failure. About the stress-strain relationship. Stress-strain relationship. Modulus of elasticity, which is capital E. That equals, the formula is very simple, is stress divided by the strain. We have to use these formulas for stress and strain to find the modulus of elasticity. See page 56. And there's a chart at the very top, figure 413, for the modulus of elasticity in pounds per square inch for those different materials. Now, if you look it up in the machinist handbook, you'll get a whole chart of many more materials. Poisson's ratio. Poisson's ratio states that when a sample of material is stretched or pulled in one direction, it tends to get thinner in the lateral direction. And if a sample is compressed in one direction, it tends to get thicker in the lateral direction. Poisson's ratio is mu, little Greek symbol there, equals the negative lateral strain divided by the axial strain. Here's an example, Poisson's ratio that's in your book. As the force is applied, the opposite sides either increase or decrease.